Zach, would you like to introduce Patrick?
Great, great work, Terrence. Patrick has been, Patrick was sort of the first person to, um, one of the first people to learn how to use NERPy. And as a result of his feedback, NERPy has been improved enormously. Um, One of his first projects was to make a clone of the VialScale 4 Einstein Toolkit Thorn, which he'll tell you a little bit more about, but using NERPy Plus instead of Crank. So go ahead when you're ready, Patrick.
Thank you. Guys see my screen and hear me okay?
Looks good.
Yes. Yes.
Okay, thank you. Okay, so yeah, as Zach said, today I'm going to be talking about a NERPy Plus clone of VialScale 4, which we have named creatively VialScale 4 NERPy. So the VialScalars are a set of 5 complex scalars that encode information about spacetime. They are contractions of the Vial tensor, usually written as C, with some null tetrad. The Vial tensor itself is a rank 4 tensor that's related to the Riemann curvature tensor.
Patrick, we're losing your audio.
Riemann curvature tensor encodes information. Sorry, that's okay. Can you hear me now?
Yes.
Okay. So yeah, while it's related to the Riemann curvature tensor, while the Riemann curvature tensor encodes information about the volume and shape of a body, the Vial tensor really only encodes information about the shape of a body. And it has the same symmetries as the Riemann curvature tensor, which gives it 20 independent components that will need to be coded. This makes it possibly one of the most complex expressions computed in the toolkit, scalar Psi4, because it is used for gravitational wave extraction. Its real and complex components correspond to the 2 different polarizations of gravitational radiation. So VialScale 4 computes all 5 VialScalars as well as some invariants that are computed from those scalars. And it does this by computing using the Crank code, which is a Mathematica-based code that takes as inputs the tensorial equations in an Einstein-like notation, which is, of course, similar to what how we actually write those expressions, as I had a little equation on the last slide. So why would we want to use automatic code generation? Why not just go writing the codes ourselves? Well, as I mentioned before, the expressions are very complicated, and doing this by hand would be impractically complicated. So we automate as much as we can in order to reduce the human error in transcribing these. And the tools like Crank code and NERPy allow us to write these expressions using a syntax that's much more familiar to how we actually write these equations out in papers. So why then, when we have a completely operational VialScale 4, would we want to write a clone of that in NERPy? The biggest issue comes down to expense. So while Crank itself is open source and free, very expensive license. On the other hand, NERPy uses Python, which is itself free, as well as the open source SymPy package. So that right there is already a lot less money to spend to get started. Everything else in the infrastructure is free and open source. Like Crank code, we have an Einstein-like notation as input, and the output is highly optimized C code kernels that make use of tools like single input, multiple data, single instruction, multiple data, SIMD, and common sub-expression elimination, or CSE, to optimize the codes. We also document everything in a lot of detail in user-friendly Jupyter notebooks that allow us to use LaTeX and HTML to make the documentation more readable and also intersperse it with our code, which allows us to reduce the human error in transcribing these equations quite a bit. So here's an example of that Jupyter notebook documentation. So up at the top, we have the full expression for the Riemann curvature tensor, which we need for the Weyl curvature tensor. And then down below, we have the code that we use to write that, to code that expression up. As you see, the two sets of nested for loops that loop over all the indices and add on the derivatives of the metric tensor and the Christoffel symbols and all the combinations thereof. And we can also see critically that on basically any screen, you'll be able to look at this teched up version of the expression for the Riemann curvature tensor and write the code at the same time without having to flip back and forth between different windows or scroll up and down, which makes coding up these expressions just a lot simpler. So then, once we've written up all of those expressions in a nice Python module, we can move on, and we'll do this in a separate notebook just to keep things organized, and write the ETK Thorn. So the first step to do after we have those expressions is going to be to import them into our new notebook and use the built-in utilities to generate the basic C code kernel, and then we can use the NURPy function, outC function, to create a C function. So all we have to do is specify the inputs and the outputs, give it a name, tell it where to put the file, and then a few other parameters for like the loop over the portion of the grid we care about, and it creates that function for us. And of course, we will need to write the CCL files for the Thorn. So this one is fram.ccl, which, as Terrence mentioned before, we now have a tool to do automatically. But this was my first project on the toolkit. So way back then, we didn't actually have that, which is why this one is written out manually. But it does also give me a chance to show off the write file. It's called the Cell Magic in Jupyter. If you note at the top, you have the 2% signs and write file. So that allows us to store raw text in the notebook and then automatically output that to a file whenever somebody runs the notebook to generate the full Thorn. So once we have output our Thorn, we of course need to validate the expressions and test it, make sure everything works right. So we did 2 tests with this to make sure everything was running as we wanted. So the first we did was an analytic comparison of the 2 expressions. We did this using Mathematica because SymPy has built-in utilities to output the expressions in a Mathematica format, while the reverse isn't really true. So we put both sets of expressions into the same Mathematica notebook, obviously changing names so that there wasn't an unfortunate collision. And we subtracted the 2, simplified the result, and found that we had perfect agreement with a nice output of 0 in the difference in the symbolic expressions. Then we also did a numerical test where we set up a simple head-on collision using Brill-Lindquist initial data for 2 black holes, and we let that run for a while and output the really all the Weyl scalars and invariants after the merger, and validated that we got basically the same thing out of both. So here we have a plot demonstrating that. So this uses the real part of the psi4 scalar. And on the y-axis, we have the significant digits of agreement between the original Weyl scale 4 and our new Weyl scale 4 NURPy's output of the real part of psi4. and this is just along the x-axis as output by the toolkit. And we see that we have good agreement between the two, hovering around 8 digits of agreement between the two codes. And we see the same level of agreement throughout the rest of the grid, as well as in the other 4 Vial scalars and all the invariants that we output. So the next steps that we would want to do are, is that the way we do this in NURPy, we are in a good position already to move this into arbitrary coordinates, simply by following the comma goes to semicolon rule and replacing derivatives with covariant derivatives, which will be quite useful as spherical coordinates are coming to the toolkit soon. And then on this slide, I also have some links to the 2 notebooks that I was talking about in this. If it would be useful, I can paste them into the chat. Okay, so that was all I had. Thank you for your attention. Does anybody have any questions?
Does anyone have any questions? So we have in the chat, we have, is there any performance difference between the crank version and the NURPy Plus version?
I didn't actually measure that, but I would imagine based on all the other steps we've taken to optimize things, it would be at least comparable to the crank version.
Okay. There's a request that you paste your links into the chat, the links to the notebooks.
Do that real quick.
Are there any other questions? All right, thank you, Terrence and Pat, for your talks. Our next, we have another question. Can it be adapted to Newman-Penrose formalism? Is there any difference? Well, can it be adapted to Newman-Penrose formalism?
I'm not entirely sure what that would entail, but I can't imagine it would be too much of a difference for the Newman-Penrose formalism. And I use the same null tetrad, the other question, as in the crank version.
Okay, thank you. All right, so our next and final item is the panel discussion with the Einstein Toolkit maintainers. How many people do we feel we need a 5-minute break before starting that?